talk of the morning. Mohammed Nawaz is going to tell us about 3D precessing jet simulations for radio galaxy Hydra A.
Welcome, everyone. Can I get this? Thanks. My presentation is on precessing jet models for radio galaxy Hydra A. So precessing jets. So we have seen some interest in precessing jet yesterday and today. So yesterday, Bizu showed a complicated megaparsec scale jet structure with the idea of precessing jet, and he estimated the length-Haring precession period for the source of 10 to the power 8 mega-year. And today, Blundell shows some nice movies of ballistically precessing jets, replicating the helical structure of SS477, SS433, thanks. So I've been also studying a complex radio galaxy, which has a beautiful asymmetry. So here, so this source is called Hydra A. So the galaxy is here, and we have a jet lobe structure, northern and southern side, and a beautiful asymmetric structure. So the aim of my study is to provide better understanding of jet energetics, jet composition, components, and estimate jet velocity, and provide an interpretation for the complex source morphology and heating of the ICM, focusing the detailed model of the northern Hydra jets. And I focus only on the northern jet because we don't have enough data in the southern side. So let's see the key features of the northern jet. So inside 10 kiloparsec, we have 2 bright norths, and the jet is collimated until 10 kiloparsec, then it flares out, and downstream we have 2 more bright north, and a twisted jet lobe morphology. So the basic assumption for modeling of this source is we assume the bright norths are produced by reconfinement shocks, and in the next slide I will explain what are reconfinement shocks. And the jet curvature and twisted jet lobe morphology is produced by the dynamical interaction of precessing jet and the intercluster medium. So here is reconfinement shock. The physics of reconfinement shock is simple. When an overpressure jet turned on in the atmosphere, it expands and comes into pressure equilibrium. And after that, the jet is collimated by the external pressure. And since it is supersonic, the collimation happens by an incident shock. And as the pressure falls rapidly downstream, the Mach number increases. So we have a convergence of the incident shock. When the incident shock converges to a point, the jet axis acts like a wall. So the incident shock hits the wall and reflects back, like any shock or wave hit a wall and reflects back. So we have a reflected shock here. So the combination of the incident shock and reflected shock, they are called the confinement shock or recollimation shock. And this zone here, it is shocked and overpressured. So we have repetition of the event. And as a result, we have a series of biconical shocks until the jet is decelerated by the entrainment with the jet boundary and the turbulent ambient medium, as Perusho explained yesterday. So here are 2 nice examples of reconfinement shock. This is from laboratory jets. We can see some beautiful Mach diamonds. And this is from my simulation. We see in the log 10 pressure plot the reconfinement shocks and overpressured zone here. So the basic challenge for modeling a very extended source like Hydra A is the resolution at different length scale. So we took a bottom-up approach. First, we model the inner 10 kiloparsec of the jet, where the jet is mildly bent. So we use AXISYMMETRIC assumption, and then we parameterize that part And using that parameters, we further model the inner 30 kiloparsec and study the complex source morphology. So the jet initialization is, we use the relationship from Bicknell 1995. So in the left, we have jet power, which is fixed, 10 to the power 45 arc per second. And these three jet parameters, jet pressure, jet velocity, and jet inlet radius, they are free parameter. And the jet density parameter is calculated from this relationship. And the intercluster medium is set based on the extra data from David et al. 2001. So with the axisymmetric model, we parameterize the jet, and especially we estimate the jet velocity. And the idea comes from the classical relationship between the natural wavelength of a supersonic flow and Mach number of that flow. So this equation here, the lambda is the natural wavelength of a supersonic flow. So we performed a set of simulations to fit the jet radial oscillation and the shock location with the observed jet radial jet radial oscillation and shock location. So in the top, we have jet radius at different location along axis in blue dots, and the vertical blue dashed line at the observed shock. And in the bottom panel, we have log 10 density and log 10 pressure profile, and vertical black lines at the simulated shock location. So this is our best fit model at the end, and we have a jet velocity from the best fit model 0.8 c and density parameter 13. So now we focus on the complex morphology of the jet in the inner 30 kiloparsec. So this is synthetic radio image for 6 different models with precession period starting from 1 megayear until 25 megayear. So we see here when the precession period is large, the jet is straight until 20 kiloparsec, which is expected, and when you reduce the precession period, we get some curvature at 5 megayear, and we get a Hydra A-like curvature, and also other features like turbulent flaring and twisted morphology, and 4 bright nodes along the jet axis with p is equal to 1 megayear. So this is our best fit model. So we have jet precession period for Hydra A 1 megayear and precession angle 20 degree. So let's see the evolution of the source for a few precession time scale and when the jet is evolved well in the computation box. So let's play it. So jet is precessing, that's good. So the structure you see here, the jet is well collimated near the base, and that is because of the recollimation shock, obviously. And jet then decelerates and flares out. The lobe is continually fed by the jet, so it is gradually rising upward. And other substructure like a few other knots is producing along the jet axis, and jet sometimes split and then come into its original direction due to the strong interaction with the turbulence. So one thing from this movie is important, the morphology. The morphology is continually changing. We are not seeing the same morphology, and that is because the observation direction or the viewing direction is changing continually. So the apparent morphology of a radio source is strongly dependent on the viewing direction. So I can demonstrate that from here. So in this figure, we have jet lobe morphology for a single time step and same line of sight, 42 degree, but different viewing direction. So to illustrate that, I add 2 cone here. So the blue cone, it is precession cone, with the white arrow is with the jet axis. So the jet lobe morphology follows the precession cone, and the black cone outside, it is the observation cone. So any line lying off that observation cone has the same line of sight with the jet axis. So for example, in the top left panel, we are seeing from this direction, we say is viewing direction chi is equal to 0. So what we are looking here, the jet is emitted and it goes far from us, and following the precession cone and turning back towards the observer. So you have a Doppler boosted lobe structure here. So this kind of structure, if we use a inverted mirror symmetry, we will get a Z-symmetric structure from this first apparent jet lobe morphology. And if we increase chi, we are basically going closer to the jet lobe morphology. So the apparent jet lobe morphology will be distorted, and we will get a asymmetric structure. And further increase of chi, further distortion, and along this direction, we are actually looking through the lobe. So we end up with this structure, something like that. So which may be, that is actually between these and these, we maybe replicate it as a long tail source. So there is a famous source called NGC 326, which is an X-symmetric structure. And further increment of chi, we get the Z-symmetric structure back. So let's see our Hydra A moments, which is with line of sight 42 degree and chi is equal to 45 degree. So let's explain this similar. In the left, we have observed Hydra A, and in the right is our simulated Hydra A. So let's see the structure developed in this simulated source. We have 3 reconfinement shocks. So 3 bright knots along the jet axis and nearly the correct location with the observation. Jet flaring happens at the correct location, and the twisted jet lobe morphology, which is also similar to the Hydra A. So one thing here, the bright spot here, that is not a reconfinement shock, that is actually formed when a supersonic flow hits the cavity wall. So it produces shocks there. So it is shocked, and we get a bright knot in this location here. One concern with this modeling is we don't have the brightness as much as in the observed brightness here. And that is because of our model is purely hydrodynamic. So that may be attributed to the increase in magnetic pressure due to turbulence. So that is one thing. So heating of the atmosphere. So we know in Hydra A, there is an outer shock surrounding the X-ray cavities, and which has a Mach number 1.2, which indicates that the shock heating of the AGN is mild in the later phase. So I estimate the Mach number from my simulation. So this is log10 density profile, which shows the forward bow shock. So I get information for different location of bow shock at different time, estimate the bow shock advance speed. Using the local sound speed, I estimate the Mach number, which is 1.85, which indicates that even in the earlier stage of the source evolution, the shock heating is mild. So maybe I will skip this. Basically, this is, I estimate the precession period from a theoretical point of view, and which also I get in the range of in the range of mega year. So I'll summarize my project. So the accomplishment with my model is, first of all, I find that the bright knots of Hydra A, they are reconfinement shocks. And second, I estimate the jet velocity from the information of bright knot location and the oscillation of the jet boundary, and which is 0.8 c. And this is consistent with some recent theoretical estimate of FR1 source jet velocity by Lying and Bridle 2014. They also estimate 0.8 c for FR1 source. And this kind of estimation is first time used in extragalactic jets, so estimation from information of bright knots. And I believe I successfully reproduced the complex source morphology with inner substructures of Hydra A until 30 kPa. And we also get some gentle heating of the AGN in the earlier evolution of the source, and also a consistent theoretical estimate of jet precession period. Thank you, guys.
Okay, I think we can take just a couple of quick questions, if anyone has any.
It's something I may have missed. When you compute the velocity of the jet from the position of the knots,
Yep.
I mean, the position of the recollimation shocks also depends on the pressure ratio.
Yes.
How have you taken that into account? Just checking the radius that this expansion produces, or because I mean you have two free parameters in the
Yeah, I have pressure also free parameters. So I used pressure 2 over pressure ratio of 2, 5, and 3. So I get overpressure ratio 5 gives that the radial oscillation correctly, because if I go less, then I have a larger oscillation of the jet, and if I go more than 5, then it actually gives very closer. So yeah. Oh yes, sorry, I'm sorry.
Okay, do we have any other questions for Mohammed? Okay, since we're a little over time, I think we'll go ahead and go to lunch.